can start streaming. All right, somebody in my other class decided to ask me to buy a newer computer because this computer was getting a little bit sluggish in class, and so people started to realize, hey, your computer is actually pretty slow. That is actually true because I have a second generation i5 processor in this thing here. It gets the job done, but I think any Chromebook that you buy today can beat this computer, like really, really obviously. But that's okay. Okay, I don't really need that much speed. I can only type so fast. I think the computer speed is faster than my typing speed, and my typing speed is way faster than my thinking speed. So everything just works out. All right. So what we'll do today is to continue the discussion of parameters. So last time we talked about how the parameter is stored on the stack. Do you guys remember the recursive subroutine that I did last time that finds the power of 2? Okay. No, yes, maybe. Okay. So maybe today's example will remind you of that one, but today we'll also talk about local variables. Okay. So what I'm going to do is I'll give you a C subroutine first. So the C subroutine is for exchanging the values of two locations. The first location is pointed to by pointer A, and then the second location is pointed to by pointer B. So this is just a prototype of swap, and then we have the main subroutine, because I want to translate this into assembly and actually run it. So I'm defining these things in the same order so that this way the assembly code and the C code is kind of one-to-one. The main program is going to have two local variables on its own. I will call these xy. Okay, so x is a local variable of main, y is also a local variable of main. And then we'll have some values into these particular local variables. Let's say x starts with a value of 61, for no particular reason, and then y starts with a value of 129, and also for no particular reason. And then we want to call the swap subroutine, so we want to swap. But when you call swap like this, you have to take the address of x and also take the address of y. Okay? And then we are done. We have return 0 here. So this is main, and then the swap subroutine is nothing really too complicated. It is the same kind of swap subroutine that most of you already know, to exchange the values of two things, except this is done by pointers, because I'm not using C++, I'm using just plain C. So the typical way to do this is you define a local variable called t for temporary, and then you just say t is whatever pt pointer A points to, because this way you make a copy of what pointer A is pointing to before you destroy it. The second one is to copy whatever pointer B is pointing to over whatever pointer A is pointing to. And then the last thing to do is to overwrite whatever pointer B is pointing to with T, which was storing what pointer A was storing, or the value pointed to by pointer A to begin with. So that's a pretty typical sequence of instructions to exchange the values of two locations. And that's it. This is the C program. So do we have any questions about the C code itself? Any questions about the use of pointers and also the logic of exchanging the values of two things, which is what the swap subroutine is all about. So that's all good? Okay. Any questions about the taking the address of something, like on line 7? Because we have to take the address of local variable x, pass the address of x instead of the value of x, and the same thing with y. Is that okay? Concept-wise. So is that all okay? All right. So we'll have this program on one side, and then I'm going to open a new window to implement the assembly code on the other side. Now in assembly code, there's no such thing as a prototype, so the prototype doesn't get translated at all. Okay, because in assembly programming, there's no type, so there's no type checking, there's no need for a prototype to do any of that. So we'll start with the initialization of the stack pointer. which is subtracting register D from register D. So this is really just to initialize the stack pointer. So the stack pointer is now pointing to one location past the end of memory. So this way, when we decrement it, it will be pointing to the very top of the entire RAM, and that's the first location I will use to store something on the stack. Is that okay? All right. So the stack is nothing more than a region of memory in RAM that I designate as quote-unquote stack. And the whole concept of a stack is last in, first out. The very last thing that I put or store on the stack is the first thing that I retrieve from the stack. Are we good so far? Okay. And then the next one is just a main label. It's really just serving a purpose of commenting and say that if we had a main subroutine, this would be the beginning of that. We don't really have a main subroutine because a main subroutine implies that it can return back to somewhere, and there's no place for this to return to anywhere. So it's just main. Main is going to have a halt as its last instruction. So now we encounter the first two variables, the first two local variables. One is X and one is Y. They are not initialized, but they have to live on the stack. Okay, so that means I have to reserve 2 bytes on the stack at this point, one for local variable X, one for local variable Y. So the way to do that is really just to decrement the stack pointer without storing anything to those locations, because I'm just saying let's reserve 1 byte. Okay, so this is just reserving 1 byte for local variable X, and this is doing the same thing for local variable Y. So this is really what local variables are all about. The subroutine is the one responsible to reserve that space and kind of keep track of it. Is that okay? All right. So what we want to do, what I'm going to do here is to basically show you a picture of what the stack looks like at this point. We have local variable X at the top location or the highest location of the stack, and then we have local variable Y at the location right below that, and then the stack pointer, which is register D, is pointing to local variable Y at this point. Is that okay? So this is really just a snapshot of what the stack looks like at this point. What is the value of X as a local variable? I don't know. Not supposed to. Okay? What is the value of local variable Y? I don't know either. Not supposed to, because all I did was to reserve the space. But what is the bit pattern in that space? It doesn't matter to me. These are uninitialized local variables. So from C and C++, from cisp310, I'm hoping that you guys were told at least many times that if you have local variables that are uninitialized, they do not start with any specific value. They can be anything. Is that okay? And this is why, because all I'm doing is to say, I'm reserving this byte here for Y, for X, I'm reserving this byte here for Y, but I have no idea of the content at those locations. All right, so now the next thing we have to do is to pass these two as parameters. I don't want to mess around with a stack pointer, okay? So what I'll do is I'm going to copy the stack pointer to another register, C. So register C is just a general purpose register. I could have used register A or B, but I just, convention-wise, I use register C for this purpose. So now, Y is pointed to by D, but it is also pointed to by register C because I just made a copy, so they both point to the same location. The other way to denote this, which I think is slightly more concise, is whatever D is pointing to is whatever C is pointing to, which is local variable Y. All right? Wait, but that also is basically saying, D is the same thing as C, which is the address of Y. Does that make sense? Registered C is pointing to local variable Y. That makes register C the address of Y. Isn't that what I want on line 7 of the C code? Yep. So we will just have to push that on the stack as the second parameter. So now we decrement D Okay, this time we are reserve byte for second argument, and then we store to the location that we just reserved and put C onto it. So together, this is basically just pushing the address of Y on stack. Next, we have to calculate the address of X. What do you think is the quickest way to get to the address of X? Increment C. Because C already is an address of Y, and the address of X is really just one more than that. So we can just increment C in order to get to the address of X. So we say increment C so that now C is the address of X. Then we push that on the stack too. So decrement X stdc, and this accomplishes the pushing of the address of X, which is the first argument of the function call. Are we doing okay so far? Are there any questions about this code up to this point? So we are already talking about a few conventions. One of the conventions is we push the last argument first. So the last argument is the address of Y, and then we push the first argument, which is the address of X. That is a convention. It's an agreement between the caller and the subroutine being called. Are we good so far? So the next thing we have to push is the return address. So now we push the return address, LDI, A, or whatever, C is fine, doesn't matter which register. So main return, and then main return, so don't copy this because I'm going to insert code in between. This is just the way I write code so that I don't forget to define the label later on. Right, so, and then we decrement D, and then we do stda. So this time we are pushing the return address on the stack, and then we do a JMPI to the subroutine called swap. When the subroutine returns, it is the responsibility of the caller to clean up after the arguments. So in this case, we have 2 arguments on stack, or 2 bytes of arguments. So we have to increment D twice, and this is for cleaning up after the arguments. And then we have 2 more bytes on the stack, and those will be local variable Y and local variable X. So we have to do another 2 increment of D to balance the stack. So this is to clean up after the local variables. Then we have a halt instruction because now we're all done. So that's kind of the entire program from main's perspective. And somebody may argue, well, if we just put a halt instruction on line 20, that should be fine because a halt is a halt, which means, we have achieved what we need to do, but the stack is not balanced. Okay, so in this class, I am very specific about having a stack balanced by the time a program is done. In other words, if you have leftover stuff on the stack for the arguments, you have to clean it up. If you have leftover stuff on the stack because of the local variables, you have to clean it up. Points will be deducted if these increments or the cleaning up of the stack is not done, despite it may not lead to any actual problems. Because it's a conceptual thing, it is not always just a runtime thing. Is that okay? So yes, some people can say that I'm kind of anal about this sort of thing because, hey, the program runs, what is the big deal? The big deal is, do you understand? Are you showing me that you understand the concept that the caller has to clean up after the arguments as well as the local variables? Is that okay? Yep.
Sorry, I understand. So what do you mean by balance the stack?
It means by the time you get to the end of this program, the stack pointer should go back to 0. Where you start, it should be the same when you get to the end of the subroutine. All right. Are there any questions about the implementation of main, which is calling swap, but not really a whole lot? Oh, I forgot something, didn't I? I forgot to put values into local variables X and Y. I forgot about those 2 lines. So I'm going to go back and reinsert that code. So for the most part, you don't really have to copy the code because sometimes I kind of go back and fix my code. So instead, focusing on the concept is probably a better thing to do. So, okay, so we are going back to line 5 because I forgot about line 5 and 6 entirely. So line 5 want to put 61 into x, which means I have to calculate the address of x first. C is the address of y at this point, so I just have to kind of move it around a little bit. So now C is the address of x. I do a LDI A with 61. There's no way to around this one. And then we do a STCA. So that in return is going to implement x equals to 61. Are there any questions about these 3 lines that I have just inserted here? Register C was the address of y on line 9. By incrementing it, it becomes the address of x. And then I just store the the value of 61 to where C is pointing to. But since C is pointing to local variable x, so effectively I'm just saying store 61 to x. Is that okay? All right. And then we have to store to y. So we decrement C so that C is once again the address of y. And then we do LDI A with 129. And then we store that to whatever C is pointing to. So that basically accomplishes y equals to 129. Is that okay? So I just missed those like 4 lines, maybe a little more. 6 lines, I think. But concept-wise, do we have any questions? Line 13. So on line 13, I'm decrementing C because C was pointing to x earlier. So if you look at this picture, the address of x is 1 more than the address of y. So in order to get back to from the address of x, in order to get back to the address of y, we have to decrease C by 1 so that C is once again the address of y. Okay? So are there any other questions about the C subroutine or the main subroutine here? No questions? Okay, if there are no questions about main, we're going to start with swap. So here's a swap. It's always helpful to kind of get an idea of what is on the stack at the entry point of a subroutine. So in this case, we have pointer B, we have pointer A already on the stack, as well as the return address. So when I use this kind of picture to display what is on the stack, pointer B has the highest address of the 3, and then pointer A has the lower, and then return address has the lowest of the 3. So this is my convention. Whatever has a higher address is up. Whatever has the lowest address is down. Okay. And on top of all of this, we also know that the stack pointer points to the very last thing that we push on the stack. So that means the stack pointer, which is just register D, is pointing to the return address at the entry point of swap. Is that okay? That's the convention. That is the agreement between the caller and the subroutine being called, is the caller promises that, well, I shouldn't use the word promise, but it's a convention that the subroutine understands that by the time you get to the starting point of a subroutine, the caller would have set up the arguments as well as the return address in this particular order, and then the stack pointer is always pointing to the return address at that point. And that is what some of the code above has been doing. Yep.
So we cannot jump to swap before we do all that stuff.
Say that one more time.
So we can jump to
That is correct. Because that is the agreement. And this agreement is not something that I invent. Okay, this is actually the same agreement from all C compilers. So if you use GCC to compile a program to the ARM architecture, it is the same convention. If you use the GCC compiler to compile to the x86 architecture, it's the same convention. If you use Arduino to compile a program to run on a little Arduino board, it is also the same convention. So this convention is pretty much universal to all implementations of C and C++. Yep.
You said the pointer B has the lowest address or highest?
Highest.
Highest.
Yep.
And then, so for the function swap, you pass the address of x to pointer of A, right?
Correct.
And
So
the
pointer
x
A,
supposed to have the highest, right? The pointer of the address of x.
okay. So pointer A as a parameter has a higher value than pointer B, but the address of pointer A is actually lower than the address of pointer B. Just because it has an address type doesn't mean that it does not have an address of its own. Every parameter, every local variable has its address. Okay, so the address of pointer A has nothing to do with the actual value of the parameter. Okay, well, we're going to run this program with tracing. So when we go through the trace, we'll see actually what is being pushed on the stack. Then it will be kind of clear what we are, what this code is actually doing. All right. So the first thing we want to do in swap is to allocate a byte for our local variable. So we want to decrement the stack pointer by 1. So this way we can reserve a byte for my local variable t. So now the stack looks a little bit different, kind of the same, but we just have one more thing on the stack. Because instead of having the stack pointer, the return address as the lowest item, now we have local variable t as the lowest item, and now the stack pointer points to it. Okay? And then what do we do? Well, we're going to go implement line 14. Line 14 says, we want to get to pointer A, but we are not interested in the parameter pointer A itself. We're interested in what it points to. Okay? So we have to find out, okay, first, how do we get to pointer A? Once we get to pointer A, how do we find what it points to? All right, so typical way to do this, CPR CD, okay? So this way, C is the same as D, and we also know what D is. D is basically now the address of T, and that's because D is the stack pointer. So is that okay? That is not what I want, okay? What I want is PTRA. So if I increment C once, it is now the address of the return address. Increment it one more time. Now it is the address of the parameter that we call pointer A. So we're getting closer, okay? We're getting closer to what we need. But it is not the address of pointer A that we ultimately need. We need to get to the parameter pointer A first. So we need an LD instruction. I'm going to keep C around here because C is really useful. So I'm going to use another register. So now A is PTRA. In other words, register A at this point is the same as the parameter pointer A itself. Okay? But that is not ultimately what I need. I need what it points to. So let me see. I can probably get away with using another register to do this. Okay, so I'll use a LDBA. So now B is actually whatever PTRA is pointing to. Are we doing okay so far? So we have to get to the address of the parameter, then we get to the value of the parameter, and then we get to what the parameter is pointing to. So it's a kind of like a 3-stage kind of thing to get the right-hand side of line 14 done. Is that okay? All right. Okay. So we have the right-hand side done on line 14. Now we have to say, but where are we storing it to? We're trying to store that to T, and that can be done with just one single instruction like that. So this is basically saying T, the local variable, gets whatever PTRA is pointing to. Because the stack pointer all this time is still pointing to local variable T. We have not moved the stack pointer since we allocated for the local variable. So that makes it kind of handy. I don't have to do any computation to get to the address of the local variable T. Are we still doing okay so far? We're done with line 14. I mean, this is all just for line 14. All right. Shall we move on to line 15? Okay. So moving on to line 15, the first thing we need to get to is PTRB. Well, the register C, the last time we made any change to register C, it was the address of PTRA. And you can see that PTRA is just 1 byte below PTRB. So that means if I increment C, we will get to the address of PTRB. So we just have to do an increment C, so that now C is the address of PTRB. But once again, it's not the address of PTRB that we are really after. We are after the content pointed to by the parameter. So let me see which register I should use here. I think we can safely reuse B. Okay, so we'll do a LDBC. So the B is now PTRB, the pointer itself. But that is still not what I really want, okay? Because what I really want is the content that pointer B is pointing to. So I need another dereference like that. And this is totally legitimate. You can actually do something like that. Okay, you can use the same register as the one being dereferenced and read, and the one being changed in the LD instruction. Same thing with the ST instruction. Is that okay? All right. So that gets me whatever I need on the right-hand side of the assignment operator on line 15. Now we need to figure out where are we storing this thing to? Well, we want to store that to whatever pointer A is pointing to. Aha! Good thing I did not overwrite register A, so the register A is still pointer A. So I'm not overwriting pointer A, I'm overwriting what pointer A is pointing to. Okay, so the store instruction that is after this is storing to whatever register A is pointing to, and the source is just register B. So now this becomes pointer A, whatever pointer A points to gets whatever pointer B is pointing to. So it's very important for you guys to keep track of which register has what at any particular time, because it is on line 44 that I have set up what register A has. Register A is pointer A on line 44, and I need that back on line 51 because I need to dereference pointer A, and that's why A is being dereferenced in the store instruction. Is that okay? Now, this particular architecture only has 4 registers, which makes it relatively easy to keep track of what each register has. When you're dealing with a true RISC architecture that has like 32 or 64 registers, then it gets a little bit messy. This architecture, this toy processor only has 4 registers. So, it does run out of registers pretty quickly too, which is the downside of that. So now we're done with line 15, moving on to line 16. So line 16, well, I think we'll be fine. Okay, we just don't have enough registers to store everything, so that's fine. We don't have a problem with that. So the first thing we do is to LDA with whatever D is, because this way register A is just the value of local variable t, because D has not moved all this time. So D is really still the stack pointer, which is still pointing to the local variable t, so that's fine. Okay, so now I put it into A. Okay, the value of t is now in A, because D is the address of t, so that means I have to dereference it to get to the value of t. Now we have to figure out what we need to do with this on the left-hand side. On the left-hand side, we want to store that to whatever PTRB is pointing to. I do not have that anymore, because last time I had register B having the pointer B, I immediately destroyed it right afterwards, so I don't have that anymore. But that's okay, we can just recompute it. It's relatively easy. So once again, we just have to do a LDBC, because C is still the address of pointer B. By dereferencing C, I now have B being pointer B again, and then we can store to whatever B is pointing to with whatever A has as a value. So now this is accomplishing pointer B, or whatever pointer B points to is now storing the value of local variable t. Is that okay? So once again, the trick is keeping track of what each register has, okay, along the way. So when this is all done, okay, we have two things to do at the end of this particular subroutine. The first one is to increment D, because my local variable t should be gone by now. Okay, we are at the end of the subroutine, so all the local variables should be deallocated. So I'm deallocating local variable t at this point. So now the stack pointer, if you look at the picture, okay, let me see if I can go back up here. So this is gone, and the stack pointer is now pointing back to the return address, which is good. Okay, that's where it should be at this point of this execution. So we do LD. I can use register A this time. So A is now the return address. And once I use the return address like this, I can increase the stack pointer and deallocate the return address. This is also a convention or an agreement between the subroutine and the caller of the subroutine. And then we have a JMP A to continue execution in the caller. Continue execution in caller. That's it. That's the subroutine. So this is the program. This is the code this is the assembly code that implements the C code, observing all the conventions of the caller versus the subroutine being called. Is it tedious? Absolutely. That's why people do not like assembly language programming. But can we track it? Yeah, we can track it. I mean, it's just a little tedious. You just have to be careful and be mindful of which register has what. The most important part of understanding this kind of code is the differentiation between what is an address and what is the content of that address, and which one do we need at any particular time in this code. Okay, so all that pointer stuff that you learned in C and C++ should be coming back right about now. Yep. The parameters are not deallocated by the callee. It is the responsibility of the caller to deallocate them. So you have the parameters here, and then the return address here. So the subroutine is responsible to make use of the return address and remove it to deallocate it. And then you get back to the caller. The caller is responsible to deallocate the parameters. Is that okay so far? All right. So we're going to go ahead and assemble this program and actually run it and trace this particular program so that we can actually talk about what happens during the execution. Yes?
I keep getting the ST and the LD command always confused.
Okay. So let me address that first. Now note that I said I address, I didn't say I answered. Okay, so there are two things you need to do when you have that confusion. Okay, so you go, first of all, you go to the opcode table, because the opcode table does give you the explanation of what those two instructions are. Okay, come on. Yep, the computer is kind of slow. All right, so we look at the LD instruction, which is this one here. Okay, let me magnify a little bit. Okay, so here's the LD instruction. The LD instruction says, right here, it says, X, a register, is getting the content that Y is pointing to. So you're updating a register by reading RAM, and the location that you're reading from is dictated by Y, which is a register. That's LD, it's load. And then when you look at store, okay, so let's look at store. Where's the ST instruction? There we go. So when you look at the store instruction, it is exactly the opposite. What is being changed is a memory location. What is supplying the data to change the memory location is a register. The location in RAM that you're changing is dictated by also a register. It can be the same register. X and Y can both be A, can both be B. Okay, that's okay. But the question is, what is updated? Store updates RAM. Load updates a register. Yes?
Is it safe to say that those parentheses are, does that mean dereference?
Yes.
And also left is equal to right?
Correct. That's a convention that is consistent for all the opcodes. Is the update is always from right to left, which is the same order as an assignment operator. And then the parentheses are really just an artificial syntactic construct to emphasize that we are dereferencing that. Because without the parentheses, it's even harder to find out what is dereferenced. So with the parentheses, it is just a visual cue to say that, oh, okay, we're dereferencing that register.
So store puts it in storage, LD loads it out of storage.
Correct. Now, that is this is just an explanation, but the ultimate explanation is to look into the ROM of the processor. Okay? In other words, you just think of, okay, what about ST, and then D is register Y and A is register X. So in that case, you have 0, 0 for XX and then 1, 1 for YY, right? So the actual opcode would be F3 in that case. So then what do you do? What you do is you go into the architecture. So let me fire up the architecture first. I don't have a command line prompt here. Do one here. Start up the logic sim and then the processor. And then we go to ROM. Okay. We go to ROM, we right click, we go to edit content. We go to F30, which is the first location or the location of the first slice that corresponds to the opcode or the mnemonic of STDA, store to what D points to from register A, and that is this guy here, okay? So to study the instruction is to look at this bit pattern and then find out exactly what pathways are established because of these bits in the processor. So you have to disassemble, okay, all of these bits from hexadecimal to binary. So you end up with 26 individual zeros and ones, okay? Then what do? You take those 26 zeros and ones and you feed those 26 zeros and ones into this splitter, and then from this particular splitter, it splits into here as well. So once you decode all 26 bits, then you would also know how each multiplexer is configured, how each demultiplexer is configured, what the register bank is doing, what the RAM is doing, and so on. That is ultimately what is going to explain what the ST instruction is doing. And that is how I recommend you guys to study. And then some people may think, but that is a lot of work. Yes, I do expect you to do all that work. Okay? But can it be done? Okay? Have we talked about everything that you need to know to decode all those individual bits and find out which component is connected to which other component in which way? I sure hope so, because we talked about the demultiplexers, the multiplexers, the decoders, we talk about the registers, we talk about RAM, and we talk about the adder and stuff like that. So every single component in the entire processor have been discussed. They have been used individually. So now the question is, well, what do they do together when we establish pathways? Like this multiplexer is connecting this input to the output, this demultiplexer is connecting this input to that particular output, this register is enabled, okay? That RAM over there is selected and it is in read mode, which means the data is an output mode, and everything is routed in a particular way. That explains what each opcode is going to do. And that explanation is what I really want you guys to do is to decode the configuration of the processor just like that. Is that okay? Does everybody understand? Doesn't mean you agree to, but does everybody understand my expectation? So once again, you don't have to agree. That doesn't change how I'm going to make the next exam either. So whether you agree or not, how you want to study for this class is entirely your choice. But I'm letting you what I'm expecting, how you guys study, or expecting what you understand by the time we get to exam 2.
When will be the exam?
Pretty soon, because we are in week about 10 right now. So week 11 to 12-ish is going to be the second exam. Now, does it mean that you have to spend a lot of time to study? I cannot answer that question. It's entirely possible someone can look at this and go like, I can figure all this out on the fly during the exam. Just give me all the raw data, which is the schematic of the processor and also the ROM content. I can figure everything out on the fly during the exam. That may work on some people. Some other people may say, I'm going to have to need about a day to really truly understand what is going on with this processor, and I will need to write down some notes on my own, and I have to bring it to the test. That's fine, okay? So you have to do whatever you need in order to show me that you understand the processor itself and how the instructions are implemented. Is that okay? Now, what if you have a question? What if you have a question of, I'm not really quite sure what happens when PC mux is 3 and that instruction over there is doing something about PC mux, okay? Well, you can ask me, okay? But what I would typically do is to ask you some questions in return to guide you through the process of understanding the processor architecture. Because that ultimately is what I want you to accomplish, is to understand the processor architecture itself. Is that okay? So I don't know how much time it will take you guys to study, but it's most of the time it really is. You can write a tool, okay? I think you can write a tool in a spreadsheet so that you can punch in a particular hexadecimal number from the ROM, and it splits into the value of each individual tunnel. So this way, it just makes the whole process easier. Does it make sense? And what if I tell you that tool is already done? That tool is already done. I cannot remember the name of the sheet. But you can do it on your own too, for those of you who want to kind of do everything, reinvent the wheel. I think it is called Microcode Worksheet. But this may be doing the opposite. Yeah, so this one does the opposite of, you have to specify what each tunnel you want it to be, and then it will give you the actual code in the end as the microcode slice. So this one is going the opposite way. So we can actually figure out the no op instruction. It has a code of 10800007 and so on. How would you write a spreadsheet to do the exact opposite? In other words, you give it a hexadecimal number, from the ROM as one slice, and it will give you the value of each and every single control signal, that you need to know to understand how the processor is configuring all the connections. How would you do that? Okay, so I'm going to do this part for you. All right, so I'm just going to pick on, the ST instruction that we just talked about. Okay, so we go to that content. We still have it. So this is it. Okay, Control C, we copy this. Hopefully Control and paste work here. And then we paste. Yep, that works. Good. All right, so the first thing you need to do is to go look at, but this is a hexadecimal number. It is not a binary number, okay? Or it's not even a value. This is now a string. It is not a value. So you have to convert it into a number first in order to extract the individual bits. And the thing to do it is to say hex.hex to dec, to decimal. So you refer to this cell. Now we have the decimal, the numerical representation, numerical representation of the 7 hexadecimal digits. And then what do? You look at every single tunnel and you ask, well, which bits are we referring to with that thing? Okay. So I can get started with this. You guys can finish it once you know, how the process works. Okay. So this is the microcode slice. This is the value of slice. I'm just abbreviating here. All right, so we'll go pick, a particular tunnel that we are interested in. Let's say address mux, okay? So we want to figure out what is the value of address mux given the entire, slice. So address mux is here. So address mux is a 1-bit thing, and it is bit 16 of microcode data. But that in return is bit 19 of the output of the ROM. Is that okay? You have to remember how to read a splitter, okay? Which bit is, how we split the bits, out of a splitter. But eventually we know it's bit 19. So now we go back to the spreadsheet and we say, okay, this is ADDR mux, which is the same name as the tunnel itself. So how do we isolate just bit 19 all by itself? We can do a bit shift operation followed by a bitwise AND operator. The bitwise shift will get the bit all the way down to bit 0, and then the bitwise AND will basically clear out all of the other bits that we are not interested in. Okay. Now, of course, doing this in a spreadsheet means you have to learn how to do bitwise operations with a spreadsheet. Okay. And this is a first time for me as well. Pretty sure pretty sure it can be done, but we'll figure out. Okay, so we'll see whether the typical shift operator works or not. It does not. Okay, so we'll say That's not it. Well, there's always one way that works. It is bit 19, right? Okay, let's do it this way. We'll take this thing and divide it by 2 to the power of 19. That is the same thing as shifting 19 times to the right. Okay, so that works. Go like, well, but that is, it's a decimal number. Fine. Take the floor of that. But it's not a single bit. This is 42. 42 in decimal. It's not a single bit. How do we get rid of all of the other bits that I don't really want? Okay. So you want to do a bitwise AND. I'm not sure whether there's a bitwise AND or not. But if there's no bitwise AND, how do we do that? What is going to do the same thing as a bitwise AND? It's called a mod. So modding with 2 will isolate that. So I'm going to write on the whiteboard. Well, let's see. Yeah, because I don't need to write on the whiteboard. I'll just kind of write here. Okay. To isolate bits. Use an example here. 13 to 15. This is what you need to do. Okay. The equation should look like this. You first divide by 2 to the power of 13, because this will get rid of all of the lower bits, all the less significant bits will now be gone. Bit 13 becomes bit 0, and then you take the floor of that. And then after you take the floor, then you have the more significant bits that you do not need anymore. So you look at this thing here and go like, well, there are 3 bits that we really want, but everything beyond those 3 bits we do not want anymore. So what you need to do in this case is to mod this number, okay, with 2 to the power of 3 in this case. Is that okay? You guys want me to give you an even more closed form of this? Okay, I can do that. But then I have to make it even more more abstract. So I have to say to isolate bits. I'm trying to think of a symbol to represent it. J to K. Okay, so J is a lower number, K is a higher number. Okay, then what you need to do is to do this following thing. So you mod the floor of the microcode slice divided by 2 to the power of the lower number, which is J. And then you close to the power, and then you close the floor. And then the mod itself is 2 to the power of, let's see, K minus J plus 1. There we go. So this is a closed form formula in a spreadsheet. If you know you just want to isolate bit J to K, okay, they can be the same, by the way. So in the previous example here, J is bit 19, K is also 19. Okay, this equation will give you what you need. But I really don't know how to use a spreadsheet. Well, then do it by hand. I'm just trying to automate this process to make it easier on you, okay? But ultimately, I'm just giving you a tool to kind of help automate, make the process a little bit easier. If you don't have a tool, if you don't use a spreadsheet, you can still do it by hand. Do you guys know how to do it by hand? I think we have done it a few times already, okay? You just do. All right, so I'm just going to use this instruction. I'm now obsessed with this particular instruction. So we'll go ahead and do it by hand. So I'm pasting the hexadecimal code here. And then we just say it is 0, 1. That's for the 1 here. And then the 5 is 0, 1, 0, 1. And then we have 0, 0, 0, 0 for the first 0. 0, 0, 0, 0 for the second 0. B is 1, 1, 1, 0, 1, 1. the 8 is 1000, and then the 2 is 0010. Okay? And you just count in this case. Where's bit 19? Let's count. This is bit 0. 1, 2, 3, 4, 5, 6. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This is bit 19. You don't need a spreadsheet. It's just a little bit tedious this time. But that is what I want you to do. This is what I really want you to do, is to decode a slice from the ROM, extract all of these individual bits so that you know what value each tunnel has. And then based on that, understand how the multiplexers are configured, how the demultiplexers are configured, which register is enabled, okay? Is RAM being active? If so, are we reading from RAM? Are we writing from RAM? How are the pathways established? Then you actually understand what a particular opcode is going to do in the processor. How many opcodes do we have? 20 something. Some are really trivial, like no op. It's like, okay, that's not, it doesn't do a single thing. Halt, okay, it's pretty simple as well. There's also an entire family of instructions that you can just go like, well, we just kind of lump them together. If I understand one of those, I understand most or all of them, okay? Add, subtract, and, or, okay, bit shift. To a certain extent, not, okay? They're all going through the ALU to do some calculations. So they are lumped into one single family. All the jump instructions, especially the conditional branch instructions, if you know how JCI works, okay? JZI, JSI, JOI, and JLI, they all operate about the same way. So you just have to look at one and you understand the rest. What about JMPI? Okay, that's one instruction, but it is also closely related to all the JXI instructions. So at the very end, it's not really there's not really a lot of instructions that you have to kind of dive into individual bits to figure out how they work. It is just a few bigger families of instructions, of each family you pick a few, and then you decode it like this. You figure out exactly how the processor works, based on the individual bits of a slice in the ROM, and the more you do this, the quicker it gets. Okay, the first instruction may be very slow because you don't know where the tunnels are or which tunnel controls which multiplexer. But by the time you get to the 5th instruction, guess what? You already have a mental map of where everything goes. So it'll go faster and faster. Yep. Oh, you can just execute the instruction too. Yeah, absolutely. So you can execute the instruction, wait until that slice of ROM is outputting, to the data output of that ROM. Then you just observe the whole thing. Yes, absolutely. So you don't have to do it on dry paper. You can actually do it interactively with LogicSim. So that way you don't have to do any type of decoding into individual bits. You just have to poke the individual wires and figure out, what is the value on this thing, what is the value of this thing, and you can actually visually see which register is enabled and so on. So that's another way to do it. But you can't do that during the exam. So that means you have to kind of write down your understanding by doing the experiment, but you cannot bring LogicSim with you during the exam. But yes, absolutely, that's another way to study, another way to get a full understanding of all the instructions. Okay? So do we have any other questions about how to study or how to actually understand the inner workings of the processor? Yep.
For this example, we are looking for the bit 19. So why we are looking for bit 19?
Well, I'm just using bit 19. I'm just picking on it as one particular example.
So what if I want to trace like RI mux?
Which one? RI mux?
Yeah. So
all right. So okay. So the first thing you do is you look at RI mux. Okay, and it is bit 0 of Ucode data, right? And Ucode data is here. So Ucode data itself is bit 3 to bit 23. So this is bit 0 of bit 3 to bit 23, which means it is actually just bit 3. Okay? So if it is bit 3, then you go back to this thing here and just count. This is 0, 1, 2, 3. So you're looking at this particular bit. RI mux is 0. Now RI mux is not a single wire. It is? Yeah, it is a single wire. So it's just 0 in this case. So you go to that multiplexer and you just say that, okay, the select of this multiplexer is 0, which means it is connecting input 0 to the output. Because that's what the multiplexer does. It has multiple inputs and one single output. So the select bit, which is what RI mux is now saying input 0 is now connecting to the output. So you have to do it to all the multiplexers, so that this way you know how everything is switched around and which component ends up actually connected to which other component.
And also the method you just suggest.
Yeah.
So
Okay, so there are several ways to do it. If you want to be super duper lazy, you can just inject the code into here. You just inject F30 into here. So you're forcing the content of that particular slice to output into these individual bits. Then you can actually look into the components and go like, okay, so the ST instruction does use RAM because RAM is selected. It is going to write to RAM because LD is a 0. And who is dictating the address of RAM in this case? So you track down the address port. You look at this multiplexer. ADDR mux is a 0, which means input 0 connects to the output. Input 0 comes from this demultiplexer. This particular demultiplexer select is a 0, which means this line is connected to this line here. And then you go into the register bank and you try to figure out who is outputting to output 1 of the register bank. So you look at this output 1, register output 1, and it is being selected by register output 1 select, which is a 3 or 1, 1. So that means input 3, which is this wire, is connected to the output. That ultimately connects to register D. So register D is connected to the address port of RAM in this particular instruction. So that is how you can track down everything, by just injecting the opcode that you want to understand into the microcode pointer itself. Is that okay? Now I would not click it. I would not do single clocking, because you're really tricking the processor to do something that is not supposed to. So the execution of the instruction can cause problems because we don't have the registers set up. But at least you understand how the components are connected by doing it this way. So yes, this is yet another way to understand how the processor works. But it does require LogicSim to be around, to be running, because otherwise you wouldn't be able to inject that value in. So is that okay? I think I have just described maybe 5 or 6 different ways of studying for this class. So whichever way suits you, okay? You can print out a stack of the processor itself, and then on each piece of paper, you use a highlighter just to highlight how the multiplexers and demultiplexers are connected, and then just use another color to circle the registers that are enabled. Okay? The nice thing about that is you can bring it with you in the exam because it's on the piece of paper. Okay? Doing it this way is a good way because it's very interactive. You don't have to do all the decoding in your head, but you cannot bring it to the exam. So you can do a combination. Use this to help you gain an understanding and then document it on the printout. So now it's quick to get everything understood, but once you understand it, document it on the piece of paper, and then you can bring that to the exam. So lots of ways of doing things. So are we good so far? Okay. So the spreadsheet method is just one way to do it. Okay, it's not the only way to do it. I'm a little bit obsessed with using spreadsheets, so slightly biased opinion there. So are we okay so far? Okay, all right. All right, so getting back to the program. See, I haven't lost the context of this discussion. So getting back to this code here. All right, we want to run it. So copy and then go to my assembler. Oh, is that my only browser? Nope, there we go. Here's the assembler. See, my clock is running at 1.3 gigahertz, even though it's capable of 3 gigahertz. It's because it's running pretty hot right now. So the thermal protection part of the supervisor is actually trying to underclock the processor so it doesn't overheat and die. Another clue, I might need a new computer. All right, so it's doing the assembling. The CPU is running at about 81 degrees Celsius right now. So a little bit on the warm side. It won't die, it's just a little warm. That's why the clock is adjusting to accommodate. All right, program is all assembled. Then we go to RAM file. And download. And we'll download it as swap.csv. Yes, we are replacing it because I got the same program done slightly differently with my Monday, Wednesday class. And then we switch back to Logisim. Right click, load image. All right, so here's the swap subroutine already loaded in. I can just single clock it if I want to, or run it at full speed, but it won't show me anything useful if I did that. So it would be really helpful if I log some of the more important stuff in this particular processor. So I would definitely log the program counter because that tells me which instruction I'm executing, so which is really helpful. Register D is my stack pointer, definitely useful. Register A, register A, B, and C, they're kind of useful because I can tell what am I copying from one into a particular register with all of those instructions. So we want all of these. And then the last one we want are some RAM locations. So we look at the RAM locations and we try to figure out how many RAM locations do we need to log before we actually trace the program. In other words, we try to understand the program first before we decide how to trace the program. We know this is local variable X, this is local variable Y. This is parameter 2 of swap, this is parameter 1 of swap, this is the return address into the subroutine. This is the local variable in the subroutine. So I'm just counting all the things that I need to use on the stack just by running through the program in my head. Okay. Now I'm not expecting you guys to be able to do that all mentally because I know this program really, really well. Okay. So you might need a little bit longer time to do it, but that's the kind of reasoning that I want you to do, is to think it through and figure out how many locations you need to log in the log. So just to be safe, I'm going to log this location 2, which should not change at all, okay? But I'm going to log it just in case. So we'll change all of these locations to base 16. All right, there we go. Oh, forgot one thing. I forgot to specify the output file. So let's put it into swap.tsv, which is also going to be overwritten from the previous class. So we overwrite it and close the window. Now we can single clock, clock it at full speed. So Control K runs it at full speed. It has now stopped at the halt instruction. Control K one more time, stop the simulator. So I'm going to close the simulator at this point. And then we'll use a spreadsheet to take a look at the log. So the faster way to do it is not to use Google Spreadsheet, which is kind of slow and inefficient. So this is actually a lot faster. And it's swap.tsv that we want to take a look at. Swap.tsv. Uh-oh. Oh, this is the wrong folder. Like so. Okay, this is a trick that I learned just recently. Is you can shift select all of the columns, and then change the column type from standard to text. So this way, it won't try to convert some of the numbers from base 16 to base 10, and then some of the numbers not converted. So click OK, and now we have the log. And I would also change the heading so that this is the stack pointer, which we all know is register D. This is register A. I just don't like the heading to be so wide that it takes up too much room. Okay. This is the location. This is the content of location 255. I use this notation. The location of 254. The location of 253. The location of 252, or the content at location 252. 251. Almost there. 250. And 249. All right, then we select every single column in the spreadsheet. Okay, I just click on something else. Shift select. There we go. And then we double click at the edge to make them as narrow as possible so they can all fit on the screen. So now we have a pretty complete trace of this program. Okay. So the first thing we want to do is to go all the way to the bottom and ask, did it get the job done? How do we know whether it got the job done or not? Well, we kind of know what 255 is. So if you want to, you can actually comment in that particular column and say that, yeah, we know what column F is supposed to be. It's location 255, but otherwise we know that this is local variable X of main. We know what the next one is. It is supposed to be local variable Y in main. Okay, so knowing that, okay, let's just focus on these two columns for the time being. They got initialized to 3D and 8.1 respectively. Are those the values that we're expecting? 3D is 3 times 16 plus 13. 3 times 16 is 48. 48 plus 13 is 71. 61. Okay, so it's 61. Was that what we used to initialize variable X? Okay. The other one is 128, because this is an 8 here, which is 8 times 16 plus 1, which is 129. We initialize Y with 129 as a constant. Yes, we did. So we know the initialization part is working by analyzing the code up to here. Okay, so I'm not going to do a row-by-row trace, because everything seems to be working. So unless I have questions about how a particular what a particular instruction did, I'm not going to look into that. So ultimately, what we want is to go all the way to the bottom and see if they are exchanged. And by the time we get to the halt instruction, the content of those two were indeed exchanged. So that's good. Okay, the program accomplished what it is supposed to do. Remember the thing about I'm anal about the stack being balanced. If it starts up with 0, 0, it should end with 0, 0. So did it end with 0, 0? This is our stack pointer. It started off with 0, 0. It ended with 0, 0. So the stack remained balanced. This column was not supposed to be touched. Looks like it was never touched because it's all 0, 0. Now you cannot really tell because if I overwrote 0, 0 with 0, 0, it will not be visible. You cannot really tell that it has been updated. But one clue is, was 249 ever the value of the stack pointer? Okay, it was not. So that's a kind of good clue that we never reached that location on the stack. Is that okay? What about all those local variable thing, and how did we, actually overwrote, let's say local variable t. Where's local variable t? This is parameter 2, this is parameter 1, this is the return address, this is local variable t. Okay, so let's go ahead and make sure that we understand this is local variable t. Okay, and I'm going to use this trick here so that the header of each column remains visible as we scroll through the rest. So we scroll through this the rest here until local variable t has a value. Local variable t has a value of 3D, which is the content of where PTRA pointer A is pointing to. Is that correct? Oh, by the way, where's pointer A? Pointer A, this is the return address. This is pointer A. Pointer A has is pointing to location FF, and location FF is my local variable x in main, which has a value of 3D. So if you look at each row, it tells you exactly what is going on in this program, what is the state of everything in this program at any particular time of the execution. I mean, this is a really complete picture of what is going on when you run this particular program. Now, if you have any particular question, like, okay, pick out a particular instruction and you go like, well, I'm not really quite sure what that instruction is actually doing. Okay, so we'll pick one. And that you have to go to the Assemble tab of the assembler. So let's just say that, okay, we'll scroll down a little bit, because we want to look into the swap subroutine, and we just pick out one thing here. Okay, so we go like, I have no idea what is in register B at the beginning of this instruction and what it is accomplishing. Okay, even though the program itself was annotated and commented, we'll just go like, let's say we don't understand what it is doing. Okay, so how do we use the trace to help us understand what the program is really executing or what it's doing with this particular instruction? We go to column W, we find out what location is this particular instruction. It is location 25 in hexadecimal. So now we switch back to the trace, and then we look up the program counter until it is 26. The reason why you have to wait until it's 26 is because by the time the instruction executes, the program counter has already incremented past that location. So it is always 1 byte past the location of the opcode that you look for in the trace. So we look at this slice here, row 58, and then we ask, what is going on here? What is in each register? Well, we know exactly what is in each register, and then we compare between row 58 and 59 to understand, what is being changed. And you can see what is being changed is register B. It now has a content of 8.1, and 8.1 turns out to be the content of what register C is pointing to. So we know that it copied the content of RAM where register is pointing to override the register B with this particular instruction. Actually, I take it back. It is itself. It is FE. The content of location FE is overwriting register B itself. Because when you look at location 254, that's the one that has 8.1 in it. So that's what the LDB and then B in parentheses was doing. So we are looking at instructions from multiple perspectives. We look at the slice in the microcode, We understand the pathways, and then we understand what that instruction is supposed to do. We look at the trace of an actual program, and we also observe the same thing. It's a confirmation of your understanding of, yep, everything is consistent. Is that okay? All right. So this is the kind of things that I kind of want everybody to go through to get a really good understanding of how the processor works and how the instructions work. It is a lot of work, okay? But that's how you gain understanding, a good, thorough understanding of the processor. We are running out of time. I think the next class was trying to get in, so I'm going to stop the lecture. The lab is already activated, so by the time we get to the lab, it should be good to go.